Hi there. Welcome back to the series on Azure pipelines on Docker. In part one, we deployed containerized Azure pipeline agents to AWS ECS Fargate. We ran a simple pipeline, and then in part two, we added EBS storage to our Fargate's agents and learned about its limitations for our use case. Today, we'll continue to explore Fargate agents, persistent storage solution by hooking it up to EFS, or what is called Elastic File System. Before we get into EFS specifically, let's recap what we learned in part 2. According to AWS, ECS Fargate supports 3 types of data volumes: EBS for Elastic Block Store, EFS for Elastic File System, and bind mounts. In part 2, we explored EBS and discovered the key limitation for our use case. EBS provides persistent storage within a single task's lifetime. If we have multiple containers in that same task that need to share the data, EBS works fine, but if we need to persist the data across multiple task recreations, we have to jump through a few steps with snapshots and restoring from the snapshot. And we can only attach EBS to one task at a time. That's where I am hoping that EFS comes in. With Amazon EFS, it's a fully managed Elastic File Storage service that provides shared file storage for AWS compute services like ECS, EC2, and Lambda. It's a network file system, or what we know as NFS. So multiple ECS tasks with their containers can access at the same time. Unlike EBS, which is block storage attached to a single ECS task, EFS is truly shared storage. The file system persists independently of any container or task lifecycle. Multiple tasks can read and write to the same files at the same time. And storage capacity, this is the good thing, it grows and it also shrinks automatically based on usage. There's no need to provision a specific size upfront, unlike with EBS.
Let me highlight the key differences. With sharing, EFS allows multiple containers and tasks to access simultaneously, while EBS is a single task only. For lifecycle, EFS persists independently of tasks. With EBS, it's attached to a single task lifecycle, and we saw that when we stopped the task, the volume got deleted, unless we disable that termination policy. For access type, EFS is a network file system using NFS protocol, while EBS is block storage. And here's a big one for security. EFS does not require root access for file operations when properly configured. EBS requires root access, which is an AWS requirement, and we saw that in our previous video. For use cases, EFS is ideal for shared data and collaboration between containers, like my use case. EBS is better, I think, for single task persistent storage. There's a common misconception that EFS requires root access, or that running containers as non-root will cause permission issues with EFS. I found this when I searched online for a solution where there were people asking about getting a permissions denied and giving up or just running their containers as root. But the reality, as demonstrated by this article, so this article, which I will provide the link in the description for this video, this article provides us with the steps needed to be able to run our ECS tasks as non-root with EFS. Basically, what we will need is an access point for EFS. And why do we care running as non-root? It's a security best practice. Following the principle of least privilege, containers only have the permissions they need. If a container is compromised, the attacker has limited system access, which reduces the blast radius, and there are many compliance requirements requiring the use of non-root containers. In this video, we'll have a demonstration of how to set up our ECS Fargate tasks with EFS mounting. First, we'll deploy the infrastructure using Terraform, and we'll run our test pipeline in Azure DevOps. In the first run, I expect it to fail because of permissions issue. We will learn why we have that issue, and then we will then fix it with the proper configuration to give our ECS task the proper permission to access the EFS file share. Here we have our EFS architecture, where we first have in this orange box our EFS file system. It's our main storage resource, which is scalable. It grows and shrinks automatically. And here in this VPC box is our VPC, where we have these mount targets that's used by the EFS service so that it integrates into our VPC by creating an elastic network interface within each availability zone that we tell it through the creation of mount points. These mount targets use the NFS port 2049. So in our configuration, we will create security groups that allow inbound traffic from TCP 2049 so that we will properly create this network isolation and network protection to allow only traffic coming from our VPC to the mount targets of our EFS. Then we have the access points, which in the first go of our Terraform deployment, I won't deploy that yet because that's really what happened to me when I was testing this out. I didn't think I would need access points until I did, because now I understand why we need it and what needs to be configured to be able to access those file shares. Here is our Terraform template. And if you've watched the previous two videos on setting up ECS Fargate, you'll be familiar with this template by now because we've just reused it and added and changed a few parts, which I will highlight and gloss through the ones that we've reused from previous videos. The first two sections are the same, where we have Terraform statements and the provider definitions. We are getting our variables from our variables file in this variables.pf file. We're using our default VPC and subnets, and just again, I'd like to point out that these default subnets are public subnets. I'm only using it for this demonstration for simplicity, but in production, we never use these default VPC. We create our own VPCs with the proper private subnets in either a NAT gateway configuration or proper enterprise firewall hooked up to your subnets. ECR repository has not changed. Secrets manager, again, has not changed too. And we are getting our secret variables from our variables templates, which it gets from the tf-vars file, which is where and then it gets from our .env files. Again, there's no hard coding of secrets or credentials, which is best practice. Our KMS keys, we've just changed it from EBS to EFS. Here is our definition for the security group that we're attaching our EFS mount targets. We're saying only allow traffic coming from TCP port 2049, and only if the traffic is coming from the default VPC. this is the important bit, where we're not allowing any traffic from the internet to come into our EFS target points. And for our outbound rule for the security group, we're allowing all traffic, which in production, we don't want to have. Thinking through it now, I don't think we'll need any outbound traffic for this security group, because with security group, it is a stateful firewall, meaning our EFS, which will use this security group, will only be accepting traffic coming in. So all the traffic being initiated will be coming from within our VPC, and we already have the rule for that. All communications that was initiated by our ECS Fargate task to get file from the EFS will traverse that inbound security group rule, and so there's really no requirement for any outbound rule. Here is our EFS file system creation. Things to note is that we're using our encryption with the KMS key we've created above. The performance mode, we've got a couple of options, either general purpose or max IO. Max IO obviously will be much, much faster. We don't need it for our use case, and it's going to be more expensive. With the throughput mode, again, a couple of options there. You've got the provisioned or the burst mode. And the bursting mode is what I like because it scales automatically. It means the throughput increases as the storage size increases, and it also decreases as the storage size decreases. So unless you have the specific requirement to have a consistent throughput regardless of the size of your file share, then bursting would fit most of the use cases. We have a lifecycle policy which transitions our data into infrequent access after a certain period of time, and transitioning the files back to standard after it's accessed. Here is the mount target definition, where we're just referencing our files EFS file system ID with and saying which subnet we want to have that mount target created, as well as the security group we're using. One thing to note with mount targets, let's refer back to this diagram, is that you need to create a mount target for each availability zone. So if you have 3 availability zones that you want to use for high availability of your EFS, then you'd need to create a mount target for each one. You'll notice here, I'm just using the first subnet. This square bracket 0 says that I'm just using the first subnet from my default VPC. That's because my ECS task is also using that same subnet. IAM role for task execution has not changed, where we're attaching the AWS managed policy for ECS task execution, as well as giving it the permission to access secrets from secrets manager. Here we have another IAM role policy that we're creating for this ECS task role. This is different from the ECS task execution role, whereas in an ECS task role, this is the role that is assumed by the containers themselves at runtime. We need to give this role permissions to access the EFS, as you can see, Elastic File System client mount and client write. There is another one, which is the client root access, which in my case, we won't need because I want to run my containers as a non-root. And here is the role for the ECS task where we're attaching that policy. The ECS cluster has not changed, as well as the CloudWatch log group for our cluster. In the ECS task definition, well, most of it has stayed the same. We changed the volume name to EFS storage, and then we added this EFS volume configuration paragraph referencing the file system ID. We're saying to enable transit encryption because that is best practice. And here in authorization config, we're saying use that IAM that we're that we've defined, which is the ECS task role to assume that IAM task policy. Container definitions with the mount points has not really changed. And again, we're using that for loop for our agents, so we can define as many agents as we want. But in my variables file, I'm just define 2 agent names in there. Our mount points stayed the same except for the name change to EFS to make it less confusing. And the rest has stayed the same, with the environment variables for our Azure DevOps being obtained from Secrets Manager. Now let's look at our Docker file. Again, this is what we have taken from Microsoft. It is pretty much the same, except I've removed this commented portion of allowing the agent to run as root, because I don't think we need that. Here we're creating our user named agent and giving it an ownership of the root, including our shared storage to that, which is the mounted file share to EFS. And finally, we're switching to that non-root user called agent. So let's build the environment. I'll just quickly run this script, and then I'll run you through what it's actually doing. All it's doing is the same as our previous videos, where it's creating the demo environment infrastructure by applying that Terraform template. Then after it creates the template, it builds the Docker image based on our Docker file, which then it's pushed to ECR. After that, it creates the ECS task based on this volume configuration. It's actually, I just copied this off from our previous video for EBS volumes, and I didn't even change it because we didn't need to change anything in that ECS task definition with the volume configuration here. And finally, it runs the task based off that task definition. So let's wait for it to finish. Our Terraform deployment is done. The script is done. Let's have a look at the ECS cluster. We've got one task running. And if we look at the task definitions, I've got my revision 10 now because I've done quite a few testing to get this right. What we're interested in, because the rest have stayed the same, is the volume statement here, where now we've hooked up to Amazon EFS as a volume, and it's referencing the file system ID. As you can see, there's no access point defined. We're using IAM authorization, which means it's using the ECS task role that we've defined the policy for, that gives it that client mount and client write access. If we click on that FS ID, it takes us to the EFS, and it uses those attributes that we've defined for performance mode, for throughput mode, the lifecycle management, and the network here. We've defined for it to use the first one, which so happens to be the availability zone 3. We would just want to make sure that when the task gets created, it gets created in that same availability zone. That's very important because I ran into this issue where my task was running in a different subnet or availability zone as the mount point. So this is our running task. It's using that task role and that task execution role. It's using the security group as well as, well, it's using the default security group. It's our EFS mount target that we've defined the inbound rule for NFS port 2049. But the important bit here for checking within our ECS task is that it's using this same subnet, which is ending in 9B165. And we've confirmed that it is using that same subnet ending in 9B165. Here is the EFS security group demo that I've created with that inbound rule, which we can quickly look at if we go to VPC, security groups, and this is our EFS security group demo with our single inbound rule, allowing only those coming from within our subnet, which is this default VPC CIDR, as well as this TCP port 2049 for NFS traffic. So if we run our pipeline, if you've seen the previous videos, you're familiar with this, but I'll just quickly run through it. We basically have three main stages: the build, the deploy, and verify using two agents. So agent 1 does the build, agent 2 does the deploy, which it takes the dummy application files that agent 1 built. It takes it from that shared storage. And lastly, we have the verify stage to prove that agent 1 can retrieve a file that was created by agent 2 in the deploy stage. So build stage, it's just creating some demo files in that shared directory. So first creating it in a temporary file, zipping it up, then moving it to the shared artifact path. And then we're using agent 2 to deploy the artifact from the shared artifact path, then writing a deployment metadata back into that shared path to test and make sure that our agent 1 is able to retrieve that metadata text file. As expected, this pipeline failed due to this permission denied error. When it's trying to create a directory, so when this agent running on container 1 tried to run the make directory command, it got a permission denied on that EFS mount file share. And here's why. To understand that issue, we need to understand that our container is running an application with a non-root user named agent. When ECS mounts to EFS, EFS doesn't know about the non-root user called agent. It needs to be told that there is a user that you need to give permissions. So before we get to EFS, we need to understand what is the POSIX UID and GID is what they call it. I'll show you how I can get the POSIX UID and GID numbers. So first off, I want to do a Docker images to get my Docker image name, which is this long name that is required for pushing our image over to my ECR private repository. I'll copy that image name and I want to do a Docker run, remove this container after we're done executing the command. Then we need to bypass the entry point because otherwise it's going to run that sh script, which we don't want it to do because we just want to get the ID number of this image. And first, I want to get the root ID. If we're running as root, 0 is the UID and GID that is used to run the applications in the container. But in our case, we're using a user called agent. And by default, this is how Linux POSIX permissions work. The first user will always be 1000 UID and GID is 1000 because we didn't give it a group. So now that we know that 1000 is the UID and GID, we need to then instruct EFS to apply this POSIX UID GID permission so that our agent user can then access that file share. And the way to do that is via this EFS access point that we'll create. And to create that, I'll run the script which I've prepared beforehand. And that is called the fix EFS permissions. So what this script does is create the access point for us so that EFS now has that knowledge of the UID and GID. So here, again, you can create this manually through creating it here, saying what is the name of your root directory path and the user ID, the group ID, if there's any secondary group IDs. So here we're just saying we have this access point that points to this root directory path, the agent storage, and giving our user called agent, which EFS doesn't know the name, but all it needs to know is the UID and GID identifier. So that is now what is being passed from our container to EFS, and EFS will know that user ID 1000 and group ID 1000 will have permission over this directory path. And this is the permission we've given it, which in Linux is 7, means that the owner has read, write, execute, and the second digit is for group, which means it's got read, write. And lastly, I can't remember off the top of my head, but these two are not really relevant. 755 is just a standard permission set to give to a non-root user. So now that we've created the access point, we still need to configure something in the task definition. For speed, I will just run this script called update task, because that's what we're going to do. In the task, we'll need to define the access point. We will telling the task, use this access point when you're going to run the task, so that the ECS task will pass that UID, GID over to that access point. So what does that script do? Update task gets the values of the cluster name, the EFS ID, and access point ID, so that it can create the task definition. Basically, all it's updating is the access point ID, because the rest are the same. With the authorization config is the same, and the root directory, we're just using the root directory. That updated our task definition. We will still need to run our task. So to run our task, I'll just run my build demo environment script again, which will redeploy the Terraform template, but it's not going to change. It has not changed, so there's nothing to deploy. It's going to try rebuilding the Docker image. Again, nothing's changed, nothing to deploy. And finally, it will run the ECS task with the latest revision. So that's done. We go and look at our task. So we've got 3 tasks running here. This one, revision 9, you can ignore, because that's the very first one before I started the video that I quickly tested and stopped. Revision 10 is the one we ran with the older task definition without the updated access points defined. So I want to stop that and just retain revision 11, which it would now have our access point ID mapped into the task. Quickly looking at revision 10 volumes, no access point. So if I redeploy revision 10 as a task, it's not going to work with my purpose of not using a non-root user, because you have to define your task definition with that access point, as well as creating on the EFS side the access point. Let's go back to running our pipeline. Just make sure that our agent is online, but it should be safe now to kick off our pipeline. We've successfully gone through the build stage, so no more permissions issue with creating those files. Well, creating that subdirectory first, and then creating those files within that subdirectory. The deploy job worked as well. Here it's unzipping that file, unpacking it into these dummy files for our Hello World app, deploying those files, as well as creating the metadata file. Lastly, Agent 1 is able to verify that the build metadata, or rather the deploy metadata, was read successfully. So that's it. Let's just recap what we learned so far. First, we proved that non-root containers can use EFS. There's no need to run as root. Second, EFS access points are the solution. They let EFS know to use POSIX permissions, and we learned how to define it both on the EFS side as a access point, as well as on the ECS side as a task definition. In this implementation, we learned security best practice with a defense in-depth model, starting off from network security with security groups. Then we have identity and access management with IAM policies for our ECS task, as well as application level isolation with EFS access points. All three layers work together. And all of this combined allowed us to run our use case of having multiple Azure Pipelines agents running on ECS Fargate containers and sharing that same storage that's persistent. So regardless of deleting our tasks, we can stop this task, then create a new task by running my build demo environment script again. Task is started. This is our latest task. Let's wait for the agents to install and come up online. And when it comes up online, all I'm going to do is run the deploy stage to bypass the build stage and just prove that we're still referring to that same EFS file share, and that the file share and the data within the file share truly persists regardless of the life cycle of our ECS tasks or containers. So we can kill our containers to our heart's delight. Our data remains there when our new containers get spun up. Again, just waiting for our agents to come up online. Okay, both agents are now up there, still offline, but I'm just gonna cancel that because I forgot to select just the deploy stage. Cancel that, run a new one, and select our deploy stage. And this will truly prove that without any building of the artifacts, our deploy stage, agent 2, will still be able to retrieve the data or the artifact that was built by our previous pair of containers through a previous task and do that successfully. And that ran successfully. Okay, that's great. That's all I had for this video. I'm thinking of how to evolve this next time with additional integration with other AWS services. So we'll see how far we can take this. Thank you for watching, and I'll see you in the next video.